Very much. As she said, my name is Jeff Brown, and I work on the Grails development team at Object Computing, OCI, based in St. Louis, Missouri. I spend pretty much all of my time working on the Grails framework, and have for 7 or 8 years. So what I want to talk about this afternoon is this is a continuation of the metaprogramming talk that I gave earlier today. So the part 1 of 2 that I covered earlier was metaprogramming with the Groovy runtime. So there are kind of 2 fundamentally different types of metaprogramming that Groovy supports. One is runtime metaprogramming. So while your program is running, the metaprogramming is happening, and that metaprogramming can be doing things like intercepting method calls and adding new methods to classes, replacing methods while your program is running. So maybe there's a method in a class that does something, and while the program's running, you want to replace that method. You still want the method to be there, but you want to replace the behavior in that method with some new logic, maybe based on some conditions that you retrieve from the database, or based on some kind of runtime conditions at runtime. You can do that with Groovy's runtime metaprogramming capabilities. And I talked about a good bit of that this morning. So in this part 2 of 2, I'm going to talk about a whole different piece of Groovy's metaprogramming capabilities, and that is things you can do at compile time. Everything that I talked about this morning were capabilities that you could execute at runtime. Now I'm going to talk about some things that Groovy allows you to do at compile time. And it turns out this enables all kinds of really, really cool and powerful features. And there's a good bit of complexity involved in what I'm going to talk about. And we're going to look at some code, and I'm going to create just kind of simple examples that demonstrate some of the capabilities. But let me start with kind of a warning that there's some complexity there, but that complexity doesn't have to manifest on your application code in order for you to take advantage of these capabilities. And I'll describe some details and examples around that. For example, some of the things I'm going to demonstrate here are happening inside of the Grails framework. So the complexity is there. We've written these interesting compiler extensions and done a lot of cool stuff at compile time inside the framework. So you as an application developer write pretty simple things, and we're able to, at compile time, to read those simple expressions that you write in your source code and then do lots of interesting things with that at compile time again. And that'll make more sense once we get into this, and I can draw up some specific examples. In the talk this morning, there were not a whole lot of folks in the group who, when I asked how many of you have done Groovy development, there were a lot who had not. And these ideas, these metaprogramming capabilities, are really kind of advanced Groovy programming techniques. They're not the sorts of things you would take on in a Groovy Hello World kind of introductory to Groovy kind of thing. So I'm going to adapt how I would normally deliver this particular session and try to account for that maybe most of the audience doesn't have a whole lot of experience with Groovy. I'm still going to be able to demonstrate some really interesting and powerful capabilities. As I'm moving along, if you have any questions or comments at all, please raise your hand. We can address questions as we move along. At the end, there'll be time for question and answers. And after the session, if you want to talk in detail about anything, I'm certainly I'm here for that. So just let me know whatever I can do to help. So what I'm going to do is just kind of jump into this and start talking about some ideas, and then we'll jump over to the IDE and write some code and take advantage of some really, really cool capabilities that Groovy and the Groovy compiler offer. It turns out that this is really, I think, one of the most compelling, most exciting parts of what Groovy has to offer, and that is its metaprogramming capabilities. And I can't really select if I like the runtime programming capabilities more than the compile time capabilities. They really augment each other and solve different kinds of problems. But the metaprogramming stuff in general is, I think, probably the coolest part, certainly one of the coolest parts of the whole Groovy story. So what is metaprogramming? Metaprogramming is programs that modify programs. So runtime metaprogramming is your program is running and it's modifying itself while it's running. Compile time metaprogramming is the compiler, which is a program in itself, right? The compiler modifying your program and generating instructions that dictate what's going to happen at runtime. So we'll get into the details and see what all that looks like. Groovy's runtime metaprogramming is supported by things like the MOP, which stands for Meta Object Protocol. So the Meta Object Protocol is the part of Groovy that handles all method dispatch and all property access and all property assignments. Really, every time you invoke a method from Groovy, and that's true even if you're invoking a method on a Java object or a Scala object. It doesn't matter what language the object was written in that you're interacting with. If the interaction is being initiated from Groovy, so if Groovy is making a method call into a Java class, the MOP handles that invocation. Anytime the interaction is being initiated from Groovy, the MOP handles that interaction. And that's when you get to take advantage of things like intercepting method calls and replacing methods. All the stuff, all the Groovy runtime metaprogramming applies anytime you initiate an interaction from Groovy code. The other way around is not true with runtime metaprogramming. So if at runtime you add a method to a class, a Groovy class, and you call that method from Java, that the metaprogramming stuff doesn't apply there, right? Because the call coming from Java does not involve the MOP, right? When Java calls into Groovy code, Java is calling directly into the code that was written in the source code. When Groovy makes a method call into Groovy code or Java code, that method call is not going directly to whatever code might have been in the source file. That call is going to the MOP, and the MOP handles that interaction. And that's one of the fundamental distinctions or differences between Groovy's runtime metaprogramming capabilities and Groovy's compile time metaprogramming capabilities. So if you used runtime metaprogramming to add a method to a class, so you're not replacing an existing method, you're adding a whole new method, and you're doing that with Groovy's runtime metaprogramming, you cannot call that method from Java, right? The Java compiler won't let you compile Java code that calls a method that doesn't exist at compile time, right? So if your program is adding that method at runtime, you're not going to be able to call that method from Java. It won't work, right? The Java code won't compile. That's not true with compile time metaprogramming, right? So if you do some compile time metaprogramming to your Groovy classes, and at compile time you're adding methods to classes, now those methods are accessible from Java, right? Because you added those methods at compile time, the methods that you added are in the bytecode, in the .class file. So when you write Java code that tries to interact with that class and tries to call this method that you added at compile time, that's all perfectly valid, right? The Java compiler will look in the class file and make sure the method's there so it can compile the Java code and verify that it's valid. And that's an important kind of line in the sand between runtime metaprogramming and compile time metaprogramming. Compile time metaprogramming is just what it says. It's happening at compile time. It affects the bytecode that's in the .class file, and that has a number of implications, one being what I just described, that now those methods that you added at compile time are accessible from a statically compiled language like Java. That's not true of things that are added at runtime with Groovy's runtime metaprogramming. Grails applies compile time transformations kind of all over the place in lots and lots of places. And this is a piece where I'm going to change things up a little bit. Let me just open an editor, and I'm going to say inside of a Grails application, you've written a controller that looks something like this. You've got an index action, and it does some stuff. It doesn't really matter what's in the index action. And you've got a delete action that also does some stuff, right? So this is the code that you've written in your project. So this is a controller inside of a Grails app. So you write code like that, and the part that's commented out around line 4 and 8, that's just where your business stuff is. You do whatever code is in your index action is there, and whatever code is in your delete action is there. But you write code like this. And let's say that one of your rules is that in order to execute the delete action in this controller, you want to make sure that the HTTP request method was a delete request. So for example, you should never delete things in response to a GET request. So maybe we want some imperative logic here that says if request.method is not equal to delete, then this is invalid, right? So I want to say response.send error 405 and then return, right? And then otherwise carry on with my logic. So the code there around lines 8 through 11, what that says is if this controller action was invoked as part of a request that was not a delete request. So I'm talking about the HTTP request method, right? It could be a get, a push, a get, a put, a post, a delete, head, trace, all that. I'm saying here in code that I'm writing in my application, I'm saying this action is only accessible via a delete request, right? So this will work, right? And it's safe. So now if someone sends a get request to this action, it won't work, right? They're going to get a 405 and they're not going to be able to modify my database in response to a get request, which is good. But that code that I've highlighted there, lines 8 through 11, that's something that will show up in lots and lots of controller actions within this controller and then across all my controllers. That's code that'll show up all over the place. So that's kind of tedious imperative logic. So Grails helps with that by supporting this thing called allowed methods. So you can say allowed methods, delete, delete, and let's say that there's a show action and it's accessible via get and so forth. Something like that. So now up on line 3, where I've defined that allowed methods, in a, not an imperative way, but in a declarative way, I've expressed that the delete action, right, this right here represents the name of an action in this controller. That delete action is only accessible via an HTTP delete request. And the show action is only accessible via a get request, and so forth. So now with that, Grails will impose this rule for you. You don't have to put that code inside of your controller action now. You instead of writing this code, which I'll comment out now, instead of writing this, right, you do this, declaratively express the rules, and then Grails imposes the imperative stuff to say anytime the delete action is invoked, if it's not a delete request, send a 405, right, an invalid HTTP request method. So in early versions of Grails, the way this was implemented is the part of the Grails framework that's going to execute this action goes to look in the allowed methods map before executing the action to see if these rules have been violated or not. And if the rules have been violated, that part of the framework would send the 405 and never invoke the delete action. In recent versions of Grails, we're able to improve on that. You get all the same behavior, but it's implemented differently in the framework. And specifically what's happening is in recent versions of Grails, we handle this not at runtime, but some of it's handled at runtime, but we've got a compile time AST transformation that when this controller is compiled, what that AST transformation is doing is looking to see if this allowed methods property exists. And if it does, when this controller action is compiled, we go look in this map and recognize delete is here, and the person who wrote this code expressed that this is the only HTTP request method that's valid for this particular controller action. So at compile time, we add this code to your controller, right? So if you write your controller as you see it here, right? You wouldn't have this code here. You write your controller and you compile it. Then if you use the Java decompiler to decompile the .class file and see what's in the .class file, you would see that this is actually in the class file, even though you never wrote it. That's added to the bytecode because of an AST transformation that's inside the Grails framework that knows what to do with what you've expressed in this allowed methods property. Right? So now we've taken some interactions that used to have to happen at runtime and moved some of those interactions to be compile time, which is good, right? So you're going to get the benefits of maybe slowing the compiler down a little bit. It's totally negligible. You're never going to measure it, but the compiler is spending a little bit more time than it otherwise would have. But now the runtime has less work to do, right? Because when this delete action is executed, we don't have to go look at this map to see if delete is represented. That's already been accounted for at compile time. So we've been able to sort of front load some of that cost. So instead of paying a runtime penalty, we've paid just a really, really tiny compile time penalty to sort this out and figure out if we need to put this code inside of your controller or not. So that's one example of a compile time transformation. There are lots and lots of compile time transformations that happen inside of Grails. What I want to do kind of as the next step is jump into an IDE, and we're going to write an AST transformation that, well, we'll see what it's going to do. So I should back up a little bit and talk about AST transformation, right? So I've used that term several times already. AST stands for Abstract Syntax Tree. Abstract Syntax Tree. So the way the compiler works, and this is fairly common, lots of compilers behave this way, but the way the Groovy compiler works is it reads your source files and parses all the characters that you typed into the source files and writes a bunch of stuff into a .class file that represents what you had typed into the source files, right? That's what the compiler does. It reads your source files and generates .class files. But there's a bunch of stuff in the middle there that has to happen. So the compiler reads your source files and then has to do a bunch of stuff, and then eventually it can write the .class files. And that do a bunch of stuff, one of the things that happens is the compiler has parsed all of your source files and it knows what you've typed in there. The compiler has to create a representation in memory of what you've expressed in your source files. So for example, if you had a method called do something, that would be, when the compiler parses this class, the compiler is going to recognize that, and it's going to create in memory. It's not going to create a widget object, right? The compiler would never create a widget object, but the compiler is going to create a representation in memory of what the widget class looks like. And that representation in memory would include things like what is the parent class of widget? And in this case, we didn't express a parent class, so the parent class is java.lang.object. And what methods are in the widget class? Well, there's a method called do something, and it accepts no arguments, and it returns void, and whatever instructions are inside this method are included in that kind of metadata. But that model that the compiler is building up that describes your classes is called an abstract syntax tree, right? So the compiler's read all your source files and created this abstract syntax tree that represents everything that you've expressed in source code. An AST transformation is what it sounds like. It's a thing that transforms that abstract syntax tree. So you get to write code, and typically application developers wouldn't have to do this. If you were writing a framework, you might take advantage of this. This is what I was alluding to earlier when I said we're going to talk about some things where there's a fair amount of complexity, but don't be scared off by this. This complexity is kind of isolated where it makes sense, and then as the application developer, you get to take advantage of that complexity without that complexity manifesting itself in your code. So as we build out this example, we're going to see the complexity, and then we'll be able to back away and see the benefit of the complexity from the perspective of the person that didn't have to write the complicated stuff, right? So an AST is this representation of your classes in memory at compile time, and an AST transformation is a thing that transforms that AST, that modifies that representation of your classes at compile time. So what I want to do is I want to write an AST transformation that will add some stuff to this widget class, right? So I have so we've got an annotation called magic number. And the annotation is mostly empty. I'm just going to annotate this class, the widget class, with magic number. And what I want one of the effects of that is I want some special properties to be added to the widget class at compile time because this annotation is there. This annotation is going to trigger an AST transformation, and that AST transformation is going to modify the widget class. It's going to put some interesting stuff in the widget class. So let's just say, make an assertion like that. So if I create a widget and ask it for its magic number, I expect the answer to be 42, right? That's the magic number that I want, that's the value that I expect the magic number property to be. Notice that there is no magic number in this class, so one thing I could do is that, right? I could declare a property and assign it a value of 42. That's not what I want to do, right? There is no magic number property in the widget class, or at least there's not a magic number property in the source code for the widget class. But we're going to write an AST transformation that will add a property to this class, and the value of the property will be 42. We'll just hard code it to be 42 to keep it as simple as I can. So this annotation is what's going to trigger that AST transformation. So we're going to say anyone who adds the @magicNumber annotation to a Groovy class, the effects of doing that is that class will have a magic number property added to it at compile time. So let's take a look at the magic number annotation, and there's really not much to the annotation. There's this, it's an empty annotation, right? There are no attributes. It's an empty annotation. but the annotation is annotated with Groovy Ast Transformation class, and then there's a name of a class. That's important. That tells the Groovy compiler that anytime it encounters a Groovy class that's annotated with magic number, the compiler should apply this transformation to that class. Okay, so back up and kind of draw these lines again. So we've written a class called widget, and I've annotated that class with the magic number annotation. Right? That's what the application developer has done. Then the folks who provided the magic number annotation, right? We've written this magic number library that you're using. From this perspective, you're an application developer using the magic number annotation. The person who wrote the magic number annotation has expressed this. And again, what that is expressing is anytime the Groovy compiler encounters a class that's annotated with magic number, have this transformation applied to that class. So magic number transformation is what we're looking for here. And here is that magic number transformation. So it's mostly empty right now, but we're going to put some code in here that does a couple of interesting things. So magic number transformation implements Ast Transformation. That's an interface provided by Groovy. This is where the scary complexity is going to show up. And again, this is not, the complexity that we're about to look at here does not manifest when you're taking advantage of the compile time of the Ast transformation. This is what the code looks like from the application developer's perspective. This is the complexity that someone has to author. Whoever's coming up with this magic number library is building this Ast transformation. All right, so in the annotation, we told the Groovy compiler, anytime a class is annotated with magic number, apply this transformation to that class. So the magic number transformation will be applied to the widget class because the widget class is annotated with magic number. So the way the Groovy compiler is going to interact with this Ast transformation is the Groovy compiler is going to invoke this visit method and pass us some AST nodes, and it's going to pass us a source unit. The source unit is stuff we don't have to be concerned about for what I want to look at. The first element in this array of AST nodes is going to be a node that represents the annotation itself, and we're not going to interact with that. The second element in that array is going to be the class node of the class that was marked with the annotation. So in our case, this class node is going to be the class node that's associated with the widget class. Not magic number, but widget, the widget class, right? The class that the magic number annotation was applied to. So that's the thing in this array that we're interested in. The second element in the array is the class that's being compiled, the class that had the magic number annotation applied to it. So let's create something really simple here. So I'm going to create a new statement. We want to do that. CONSTANT, there we go. All right, so I'm creating a statement. So in the AST are lots of nodes, right? There are class nodes, and there are annotation nodes, there are statement nodes, there are method nodes. The AST is this tree of nodes that represents everything in your source code. Every line of code that you might type in your source file, like println something or int x equals 5, there's a way to represent all of those things in some node or some piece of this API that's provided by the Groovy Ast transformation stuff. So for example, if you ever had the literal 42 in your source code, the way you can represent that in an Ast transformation is you create a new constant expression and give it some kind of value. So if in your source code you had something like int I equals 42, you've got the literal 42 hard-coded in your source code, the compiler will create one of these, right? It's going to create a constant expression whose value is 42. So we're doing that programmatically here. We're creating a representation of the number 42 and putting it in a return statement. So it's as if you had typed return 42, right? We've got a return statement, and the value that the return statement is returning is this constant expression 42. And I'm just hard-coding the number 42 here to keep this as simple as I can. But we could have lots of complexity here. We could generate the return value dynamically somehow. I'm just hard-coding 42 to keep this as simple as I can. So we've created a return statement. Now I need a method to put that return statement in. So we're going to create a new method node. The method will be called getMagicNumber. And I forget the order of things. Modifiers is next. Let me get this typed in. And then we'll back up and talk about what all that's about. All right, parameters, null, and then the statement. Let me make sure I got these in the right order. Parameter, okay, good. All right, so what I've created here is I've created a, let me get that imported. There we go. All right, so on line 24 there, I've created a new method node. So if you wrote a method, if you authored a method in your source code, the compiler has to create a method node that represents that method. In our case, we're not dealing with a method that's in your source code. The Ast transformation is creating a whole new method that we want to add to the widget class. So we're creating a new method node. The name of the method is getMagicNumber. The method is public. The method accepts no parameters. The method does not throw any exceptions, so I'm passing null. If the method was supposed to throw exceptions, I could create a list of exceptions there. So we're not throwing any exceptions, so that's null. And then the last argument to the method node constructor is the code that's inside the method, right? And our code is simply a return statement that returns 42. So there's a whole bunch of hokey pokey and some stuff going on there that I'm doing some hand waving around. So don't be distracted by that. What you should be taking in right now is we've got an Ast transformation that is creating a new method and putting in that method return 42. Right? The method is called getMagicNumber. It's public. There's got to be a return type in there. Yeah, after I left one element out here. So right here, we need to specify the return type. We would have figured that out as soon as we ran the compiler. Okay, so the method is called getMagicNumber. It's a public method. It returns an integer. It doesn't accept any parameters. It throws no exceptions. And the code inside the method is this return statement. So now all that I need to do is add that method to the class. Right? So we'll say class node dot add method. That's it. So on line 24, I'm creating a return statement. On line 25, I'm creating a method and putting that return statement in the method. And on line 27, I'm adding this new method that we just created to the class that's being compiled. Remember, circle all the way back around to the beginning here. Widget is the class that's being compiled. And because I annotated the widget class with @magicNumber, what should happen is, because of this right here, the Groovy compiler should apply this transformation to the widget class as the widget class that is being compiled. What that transformation is doing is all the stuff that we just talked about. It's creating a method called getMagicNumber. So by the time, after this code compiles, in the widget class should be a method like this. Right? That should be in the bytecode for the widget class, but we don't want that in our source code, right? That's something that we want generated at compile time. So let's recompile our project. It's building now, right? And let's run this test and see what state things are in. There we go. That worked. So if I make an assertion that this return value is 43, that doesn't work. I make it 42, the test should pass. And if I remove this annotation and rerun the test should fail, right? Missing property exception, no such property, magic number, right? Here's the widget class. Up here I'm creating an instance of the widget class and referring to the magic number property, which is basically, it's the same thing as doing this, right? So I'll do that to be more explicit. I'm invoking a method called getMagicNumber. There is no such method in the widget class, so we'll get a missing method exception if I rerun this test. Missing method exception, no signature of method get magic number. However, if I uncomment this, now our AST transformation will be applied to that class. The AST transformation is being applied to the widget class, and what that AST transformation is doing is adding a method called getMagicNumber to the class, and the method right now is just hard-coded to return the number 42. Any comments or questions about any of that? Yes, sir. You said that the annotation passes a Java class and not a Groovy class?
No, the annotation class is a Java class.
Oh, yeah, so this could very well, so that's a good catch. So the annotation itself happens to be written in Java, but it doesn't have to be, right? It could just as well be written in Groovy. And in this particular case, it would be exactly the same, except I wouldn't need the semicolons at the end of the import statements. Right, but yeah, the annotation could be written in Groovy. The AST transformation can be written in Groovy or Java, it doesn't matter. Where the language is important is this class has to be written in Groovy. Right, AST transformations cannot be applied to classes written in Java. They can't be applied to classes written in any other language other than Groovy. So Groovy AST transformations can only be applied to Groovy classes. That's it. That's the limitation. So the annotation could be written in Groovy or Java. The transformation could be written in Groovy or Java. If the transformation has a bunch of helper classes that it's using in order to do the transformation, it doesn't matter what language any of that stuff is written in. The only piece of the puzzle that's where the language factors in here is the AST transformation can only be applied to Groovy classes. So in this case, the widget class has to be written in Groovy for any of this to work. Yes?
Can I also remove stuff from AST?
You can. The question is, can you remove stuff from the AST? And you can. So you could say, we'd have to come up with some kind of rule that describes what we want. But so we'll skip that adventure and just say this transformation. In this case, we're adding a method. There's also a remove method. There's add interfaces. There's all kinds of stuff you can do to mutate the class or mutate anything in the tree, in the abstract syntax tree. So when you interact with a class node, here on line 27, what we're doing is we're adding a method to the class. I could remove a class. I can make the class implement interfaces. I can add methods to the class. I can make the class implement traits. I can change the class's superclass. I can do all that kinds of stuff, including removing methods, right? So you have to be careful. A lot of this stuff is it's really powerful, and there's lots of interesting ways to take advantage of this. But you have to be careful that you're not doing things that create systems that are impossible to reason about. So if there's an AST transformation that's removing all methods called Jeff, right? Let's just say we've got an AST transformation that's doing that. As the author of this class, if I add a Jeff method and I put some stuff in here, and that Jeff method's not there once the class is compiled, that's confusing, right? Well, I wrote the Jeff method, right there it is. Why isn't it available at runtime? Why isn't that Jeff method in the bytecode? And the answer might be because we've got an AST transformation someplace that's removing that method. So you need to have a good reason to do that, but absolutely. So you can remove methods, you can remove interfaces, change all those things I mentioned earlier. You can do all that stuff in an AST transformation. Got lots and lots of power and flexibility, and you can do all kinds of interesting things. Yes?
Once you get the bytecode, can you use it to run other Java classes?
The question is, once you get the bytecode, can you use that to run other Java classes? Is that the question? So what is it that you mean when you say, once I get the bytecode?
Once it's compiled and the transformation applied,
Yep.
I believe the bytecode has the new export. Can you extract the bytecode somehow and then use it to run other classes with this bytecode?
Yeah, so I'm not sure I understand the question, so I'll speak to it a little bit, and then if it's still not clear, I'll be happy to take it up with you offline afterwards. But the bytecode can do anything the bytecode can do, right? So bytecode can do things like interact with other Java classes. You can have bytecode that creates an instance of a Java class and bytecode that invokes methods on that instance of a Java class. Your AST transformation could be creating instructions that do all that stuff. So you can create an AST transformation that does things like creates an instance of some other Java class and then invokes methods on that some other Java class. Your transformation could generate all of that, and then at runtime, those classes all have to be there, or the system won't work. So I'm not sure if that really addresses the question, but as I said, if not, I'll be happy to drill into the details with you after we're done here. There's another hand over here. Is there another question? No? Good. All right. So we've got this trivial AST transformation in place, and all it does is anytime you annotate a class with that magic number, the AST transformation is adding a method to that class at compile time called getMagicNumber. So if we were to look on the file system and find widget.class and then decompile that with a decompiler or inspect the class with JavaP or something, we'd see in the bytecode, in the .class file, there really is a method called getMagicNumber. We're not taking advantage of any of Groovy's runtime, cool metaprogramming stuff. Everything that we're discussing here has all happened at compile time. That getMagicNumber method is in the bytecode. I can write a Java class that calls that getMagicNumber method because it's in the bytecode, right? It's just as if, as far as the Java compiler is concerned, it's as if I wrote this in my Groovy class, right? So in the bytecode, there really is a method called getMagicNumber. Right. So our example is just kind of a trivial example to allow us to explore a little bit of the API. Inside of Grails, there are lots of interesting ways that this comes into play. So for example, in a Grails application, if you declare a domain class, let's say you've got a domain class that looks something like that. So it wouldn't be declared in the source file with a test, of course. So that this is a person is a class that's inside of a Grails app, and it's out under Grails app /domain. So don't be distracted by that. You've got a domain class called person, and it looks just like you see here. There's no methods, it's just what you see here. There's an AST actually there's several AST transformations that get applied to all of your domain classes in a Grails application, and those AST transformations do various things. One of the things that an example of a method that Grails adds to all of your domain classes is it adds a static method, a public static method that returns I don't remember if it's an int or a long, but it's a method called count. Right? So all of your domain classes have a static method called count. And you can call person.count, and what you get back is a number, and that number tells you how many instances of the person class exist in the database. So in your application code, you don't write SQL, you don't write HQL, you don't write any query code other than you invoke a static method called count on an on a domain class, not an instance of the domain class. It's a static method. So you would call person.count. And what's returned is the number of persons that are in the database. There's an AST transformation provided by the framework that adds that count method. Right? So you don't do anything to make that happen. It just happens on your behalf. Right? The framework is imposing that on you. Right? So all of your domain classes have that static method. That static method is generated by an AST transformation. I mentioned the controller thing. Right? So there's an AST transformation that generates all of this code. So in this case, we're not creating a new method, and we're not replacing an existing method. We're modifying an existing method, right? So what the AST transformation is doing is getting all the code that was in your delete action, and it's inserting, before your code, it's inserting all of this. So a bunch of stuff is happening inside the delete method before your code, right? We're doing checks to make sure the HTTP method is valid, and there are other examples of that, but allowed methods is one of the things that Grails is currently handling via AST transformations. There are lots of other examples. So inside of a controller in a Grails application, you can declare a method that accepts some exception type. All right, so let me get rid of some of this and simplify our code. So if I declared a method called handle SQL problems, like that. So I've got a method. The name of the method could be anything. The name, there's nothing special about the name of the method. So I've just called it handle SQL problems. One thing that's significant about this is the argument type to the method. So if in a Grails controller, if you declare a method that accepts an exception type as an argument, so anything that extends exception, so SQL exception meets that criteria. If you declare a method like that, we've got an AST transformation that will recognize that, and what the AST transformation is going to do is it's going to do this. It's going to take all of your controller actions, and inside all of them, it's going to wrap your code inside of a try-catch block. And in here, what's happening is it calls handle SQL problems E, right? So all of your controller actions that are in this controller now have a try-catch block added to them. So this is all the code that you wrote, everything that's in line 7. All of your code is inside the try block. The AST transformation is grabbing all of that code and putting it inside of a try-catch block. If a SQL exception is caught, then this method gets invoked. So now you can declare in one place a method that gets called anytime any of your controller actions throw a SQL exception, right? So how do you do that sort of thing in Java? And the answer is that you really can't, right? You can't impose exception handling across a whole bunch of methods. You have to declare that try-catch block every place where you want the try-catch block to apply. Because of what we're doing with AST transformations here, you don't write any try-catch blocks inside of your controller actions. You get rid of all this. You just write your code inside of your controller action, and the compiler, the Grails extensions to the compiler handle recognizing the fact that you've got this method here that accepts an exception, and because that's there, then all of the actions in this controller have that try-catch stuff imposed on them. And I can declare other methods. I can say void handle URL problems and some other exception type here. I can declare as many of these as makes sense. Yeah, your question there?
So is it something inspired by AOP expected-oriented programming, source-cutting concerns they are addressing here?
Yeah, so the question is this something that was inspired by AOP, or aspect-oriented programming? And the answer is sort of, right? This solves some of the same kinds of problems that you would otherwise have to use AOP for. Maybe a common example for AOP, kind of the hello world example that you'll often see when you're looking at documentation for some AOP library, is logging, right? Maybe in every method, anytime a method in this class is called, I want the very first line in the method to log something. It says, okay, this method was called. But I don't want to have to write this log.debug index was called. Right? I don't want to put that at the top of every single method. So I might use it in a language like Java. I might use AOP for this. I might write an aspect and have it applied to all my controllers, and then maybe a proxy is involved and all the AOP stuff that has to happen to deal with a statically dispatched language like Java. Maybe the aspect is doing all this logging. In Groovy, Groovy provides a number of alternative ways to solve that problem. So I wouldn't say that this was inspired by AOP. I would say that this solves some of the same problems that AOP solves. So if it is the fact that we wanted logging statements at the top of every one of my controller actions, what I would do is I would write an AST transformation that does all the stuff we've been talking about, but what it would be generating at the top of all of your controller actions is that log statement. Right? So you wouldn't have to use an aspect. You've got something that's actually putting the instructions right inside the method, which is nice. Yeah?
What triggers an AST transformation? What in my code I think that this line will trigger an AST transformation?
I'm sorry, say that again?
So what piece of code or what is the direction for the compiler that this statement will trigger the AST transformation?
So what do you put in your code to tell the compiler to apply an AST transformation? There are several ways to do that. One is that there's a kind of AST transformation called a global AST transformation. And a global AST transformation is what the name suggests. It's a transformation that's applied to every single class, every Groovy class that's compiled. If you write a global AST transformation, one of the things that almost always shows up in those global AST transformations is inside of this method, you interrogate the class and maybe interrogate, you have some logic here that figures out whether or not you really want to apply this transformation to that class or not. So we interrogate the class and it doesn't meet some criteria, so we just return without doing anything. A global transformation, as I said, is applied to every Groovy class that's compiled, and for certain kinds of things that might make sense. It could be that you want to write a transformation that gets applied to everything. More often, you want to write transformations that get applied in some more specific context. So rather than write a global transformation that is applied to every class and then having logic in here that figures out whether or not you want to do it, you write a local transformation and only apply the transformation under certain circumstances. So in our case, we've got a transformation that's triggered by this annotation, right? So all the details of modifying the AST and creating method nodes and return statements and class nodes and all that stuff doesn't show up to me as the application developer. What I know is when I write the widget class, if I add the @MagicNumber annotation to it, I'm going to get this cool behavior, right? I'm going to get the getMagicNumber method. There's no complexity here. Someone had to deal with had to write all this stuff. So maybe part of a library, framework, or whatever. I just need to understand as the application developer, I just need to understand the implications of having that transformation applied. In sort of related to that, but in a little bit different context, as a Grails application developer, you don't have to know anything about any of that stuff, right? You don't have to think about AST transformations. You know how the framework behaves. Like, for example, the user guide describes that in a controller, if you write a method like this, that somehow this method will automatically be called anytime one of your controller actions throws an exception, but you don't really have to be concerned with how that happens. It just turns out that how that happens is we've got an AST transformation that finds this method and then goes and puts try-catch blocks and all these things because that method exists. So how AST transformations get applied and how that sort of manifests in the application from the application developer's perspective just varies depending on the specifics, but those are some examples that speak to that. There was another question over here. Yeah, there you go. They would not, and that's just a sort of, it doesn't really have to do with AST transformations, that's just how this is implemented in Grails. So what Grails will do, what the compiler will do if you have multiple methods that accept the same exception type, is it'll generate a compile error. Say you can't do that, which is good. Rather than deferring to some kind of ambiguity at runtime. Yeah, that's correct. It throws an error at compile time, so you'll be told, hey, that's invalid, you can't do that. That's another thing that an AST transformation can do, right? AST transformations don't have to just add methods and change existing methods. AST transformations can do many things. So one of the things we could do in an AST transformation is we could look for methods whose names begin with an uppercase letter. Maybe we've got a rule that says you shouldn't have methods that begin with an uppercase letter. In fact, you shouldn't have methods that begin with an uppercase letter. But if we wanted to impose that as a rule at compile time, we could write a global AST transformation that gets applied to all of your Groovy classes. And what the transformation could be doing here is iterating through all the methods in the class node and looking for methods that accept, or looking for methods that begin with an uppercase letter. And if one is found, there's another piece of the API that I won't interact with here, but there's another piece of the AST transformation API where you can trigger compile errors. And you get to define the message, and you can do the little thing that shows you the line of code that created the error. Yeah, absolutely, you can do that sort of thing. There are a number of transformations kind of provided by Groovy. I'll just kind of quickly enumerate a few of these and describe how they work without writing real code. So for example, you can annotate a class with @singleton in Groovy. This is all standard Groovy stuff. None of this is Grails specific. So you can do this in any Groovy application. You can annotate a class with @singleton. And one of the things that happens, or what that causes to happen, is an AST transformation will be applied to that class. And the AST transformation is doing things like making the constructor private. So you can't create instances of that class. You shouldn't be able to create instances of a class if it's a singleton. So the constructor, a no-arg constructor that is private is added to the class. What else happens? A public static member called instance is added to the class. So if you write a class called bank and you annotate the class with @singleton, the Ast transformation will add an instance property to the bank class. So now you can refer to bank.instance, and that will be the singleton instance. That's just one example of an Ast transformation that's provided by Groovy that solves a simple problem, right, or a common problem. So if you're writing singletons in your applications, you've got this template that you follow. This is how we write singletons, right? We have private constructors, we have a public instance variable, we've got the lazy initialization stuff that most of you are probably familiar with writing. In Groovy, you can skip all that stuff, right? Just write the class, forget about the fact that it's a singleton, write the class like you normally would. Put whatever properties and behaviors in there that make sense. Don't worry about the constructor, don't worry about the instance, don't worry about the lazy initialization stuff. Write the class as if it weren't a singleton, and then annotate the class with singleton, and the Ast transformation does all the tedious stuff, right? Likewise, immutable, right? So if you want a class to be immutable, you can annotate it with immutable, and that Ast transformation will do things like not allow mutators that would otherwise be generated for all of your properties in your class. Those mutators will not be created for that class because the class is supposed to be immutable. Yeah, so those are examples of Ast transformations that are provided by Groovy. So the Grails framework imposes lots of Ast transformations in different places. We've talked about a few of those. You can write your own Ast transformations, and there are Ast transformations provided by Groovy that do interesting things like singleton and immutable and so forth. Kind of the bottom line, and we're out of time, but kind of the bottom line or the takeaway here is not. So obviously we haven't gone into enough detail that you can just go off and start writing Ast transformations. The idea is to provide a sense for the kinds of things that can be done at compile time. At compile time, you can do things like add methods and remove methods and add interfaces and change superclasses. You get to mutate the representation of these classes at compile time, and that capability opens up lots and lots of possibilities. All over the Grails framework, we take advantage of this. Maybe you can take advantage of it directly by writing your own Ast transformations, but even if you're not writing your own Ast transformations, if you're building Grails applications, you're taking advantage of them, whether you know they're there or not. And even if you're not building Grails applications, you still could be taking advantage of things like immutable and add singleton. It turns out, even if you're not writing transformations, they're an important part of the whole Groovy story. So hopefully you found a lot of that interesting. It's certainly an interesting part of the language, and it enables all kinds of stuff in the Grails framework that wouldn't otherwise be possible. So it's a really important part of the language. If you've got any questions, I'd be happy to talk with you sort of offline, but we should probably wrap up because we are out of time now. So you've got a question, but I'll be happy to talk with you after if you want to come up. So thank you all very much.